This is the method integration via trig identities. What is going to happen here is typically you have an integral of trig functions, one or more trigonometric function. Often the trig function is to the square or higher power, and you want to be able to manipulate it in order to be able to integrate it. Some common identities are shared in the middle here, such as sine squared x plus cosine squared x equals 1. Then you've got some identities like sine of x plus or minus y equals sine x cosine y plus or minus cosine x sine y, and then some other ones there. These are common ones that you're most likely going to end up using. And as we progress through this video, you'll see how you might be able to recognize which one to use and when. Let's take a look at this first integral here, which is the integral of cosine x cubed. The cosine is cubed, not the x. And when I look at this, I don't know the integral of cosine to some power other than 1. But I do know that if I pull out a cosine squared, I can manipulate that into a sine term using this first trig identity up here. So I am going to view this as the integral of cosine of x times cosine squared x dx. I'm going to make the substitution for the cosine squared. Which is going to be 1 minus sine squared. And now I'm going to use a trick, and that is I recognize that if I use u substitution, where u is sine of x, so u is the trig function whose derivative is going to help me get rid of the other remaining trig function, that's going to help me simplify this. So let's go through that. I'm going to let u be the sine of x term, not sine squared, just sine of x, which means du is cosine of x dx. And when I make this substitution, the cosine of x dx term becomes du, and the bracket term becomes 1 minus u squared, because sine is u, so you've got u squared and du for the cosine of x dx part. And this is a polynomial, which is really easy to integrate. So when we integrate this, we have u minus 1/3 u cubed plus c. And then I recall that our original function was in terms of x, so I want to sub in for u with respect to what it was as a function of x. And our u substitution said that u is sine of x, which brings us to sine of x minus 1/3 sine cubed of x plus c. And that's our first solution. Let's do some more. So I'm going to take a look at number 2 here. And it feels a little similar because you have a sine to some power, you have cosine to some power other than 1. And so you might think of switching the cosine squared to a 1 minus sine squared. The problem with that is that's going to give an integral of only sine functions. And as you saw with the first problem, it's often advantageous to have two sine functions where one of the trig functions, it's often advantageous to have two trig functions. One of the trig functions, hopefully its derivative is going to give you the other trig function. So getting rid of the cosine and putting it in terms of a sine isn't going to help us. So I'm going to manipulate the sine to the fifth term. I'm going to view this as the integral of sine squared of x squared times sine of x. So the product of all of these is going to give me sine to the fifth times our cosine squared term. Now I'm going to make the substitution for the sine squared. So this is the integral of 1 minus cosine squared of x. That quantity squared. We have a cosine squared outside that's lingering. And I'm going to put the sine of x next to the dx. So now I see I've got two trig functions. I have cosine, I have sine. I know that the derivative of cosine is some function of sine. It's going to be negative sine, but I'm going to make use of that. And so I'm going to let u, so here's our u substitution again. U is cosine of x, which means that du is negative sine of x dx. And when I make this substitution, we have the integral of 1 minus u squared quantity squared. Cosine of x is u, so this cosine squared is u squared. Sine x dx is going to give us a negative du. From this point, I am going to expand and distribute the negative sign there. So 1 minus u squared. This is going to be 1 minus 2u squared plus u to the fourth. I still have to multiply that by u squared and the negative sign. So I'm going to get negative u squared plus 2u to the fourth minus u to the sixth du, which again is a wonderful polynomial. And that's going to give me negative 1/3 u cubed plus 2/5 u to the fifth minus 1/7 u to the seventh plus c. And remember, we don't want to end as a function of u. We want to get it back in terms of the original variable, which was x. Since u is cosine of x, I'm going to substitute that in. And I've got negative cosine cubed of x divided by 3 plus 2/5 cosine to the fifth x minus cosine to the seventh power x over 7 plus c. And that is our second solution. Let's continue on. Then you get to sine squared. Integral of sine squared t dt. Now this, you may initially think to substitute 1 minus cosine squared in for it, but that's still going to leave you with a cosine squared term, so some trig squared, and just flipping back and forth between 1 minus cosine squared for sine squared or 1 minus sine squared for cosine squared. It's not going to get you very far. So we need a different approach to this. And when I look through, again, the common trig identities, I see that in this second term in the middle column of identities here has a sine squared in it, and the cosine squared on the right side I could also convert into a sine squared term and solve for sine squared. I would do that because I see the cosine 2x on the left side no longer is to a power other than 1, which is advantageous. That's what I want. Having a power of 2 or higher bugs me, and I want to be able to get rid of that. So before integrating, I am going to figure out what to sub in for sine squared. I know that cosine of 2x, according to that identity, is cosine squared minus sine squared. And I know that cosine squared is 1 minus sine squared. And we still have minus sine squared x, the second term. And this is 1 minus 2 sine squares, which means using a little algebra, sine squared of x is going to be 1 minus cosine of 2x divided by 2. So that is what I'm going to sub in to our integral. Let's go ahead and do that. Our integral then is the integral of, I'm going to divide by the 2, so I've got 1/2 dx minus the integral of 1/2 cosine 2x dx. This first integral is going to give us x over 2. And this second integral, I might think, well, the integral of cosine is sine, so I may jump to sine of 2x. But this isn't quite right, because if I check and I take the derivative of sine 2x, that's going to give me cosine 2x, and using the chain rule, the derivative of the inside, so that the derivative of 2x is 2. So this is going to give me 2 cosine 2x, which I only want cosine 2x, which means I need to multiply by 1/2, which finally gets us to x over 2 minus 1/4 of sine 2x plus c. And so this one didn't require eventually using U substitution. There's a couple more problems that are moving away from just a simple sine and or cosine term. So let's take a look at number 4 here. So number 4, we've got tan to the 6th and secant to the 4th. And like we did in problem 2, I want to get rid of some of one of them, but I want to leave something that has the derivative of one of these functions. The derivative of tan is secant squared, so I could remove one of those secant squares, because right now it's secant squared times secant squared to get secant to the 4th, and that may work. The derivative of secant is secant times tangent, and so I'd have to manipulate the secant to get rid of 3 of them, and I'd have to manipulate the tangent part in order to get rid of 5 of those, which seems a lot more complicated. And so I think getting rid of a secant squared and keeping one left over is really the path to go. So we have the integral of 10 to the 4th, 10 to the 6th, x, and then a secant squared according to this second identity in the first column, secant squared is tan squared plus 1. And then we have a tan squared, or a secant squared, excuse me, left over. And now looking at this, even though it looks uglier, I realize, well, if I let u be tan of x, then the derivative is going to be the secant squared, and that's going to disappear. So I'm going to use u substitution, where u is tan of x, and thus du is secant squared of x dx. And when I make that substitution, we have the integral of u to the 6th times u squared plus 1, and secant squared x dx is du. And this expands very nicely into u to the 8th plus u to the 6th du, which is 1/9 u to the 9th plus 1/7 u to the 7th plus c. And again, we don't want to leave it as a function of u. We want to answer as a function of x. Since u is tan of x, I'm going to substitute that back in, which gives me tan to the 9th power of x over 9 plus tan to the 7th power of x over 7 plus c. I believe there is one more problem, one more example to go through, so let's take a look at this. So over here, we have sine of 4x times cosine of 5x. There's no power higher than 1. And when I look through my identities, what seems potentially appropriate is this first one in the third column here, sine of x plus or minus y's identity. And the reason is I see a sine times cosine term on the right hand side, and so I'm going to make use of that, where I'm going to assume that the x part is the 4x and the y part is the 5x, I believe was the term. Yep. So I'm going to make use of that, and we're going to manipulate here. So the identity says sine of 4x plus 5x, or 9x, is equal to the sine of 4x cosine 5x plus the sine of 5x cosine 4x. We also know that if we had subtracted instead, that 4x minus 5x is sine of negative x, and this would be sine of 4x cosine 5x minus sine 5x cosine 4x. And what made me think of looking at both of these is I realized that even though the sine 4x cosine 5x was present in the first one, it would give me back a sine 5x cosine 4x, which gives me the same type of problem that I'm trying to solve already. And so I was wondering if the second equation might be helpful, but that has both terms in there also. But what I recognize is that if I add these two equations together, then what I get is sine 9x plus sine of negative x equals 2 sine 4x cosine 5x, and the last term cancels out, which, dividing by 2, I now see that sine 4x cosine 5x is equal to 1/2 sine of 9x plus 1/2 sine of negative x. So that's the substitution that I'm going to make here, which means our integral is now, I'm going to pull the half out, 1/2 the integral of sine 9x dx plus 1/2 the integral of sine of negative x dx. So let's go ahead and integrate this. The integral of sine of 9x, 1/2 is remaining. We're going to have negative 1/9 cosine of 9x. If you're not sure where that came from, you could always use u substitution by letting u be 9x. But what I recognize is that the integral of sine is negative cosine, so that's where my negative and my cosine came from. The 9x, in order to account for that 9, I need to divide by it too. So this way, the derivative of this term, negative 1/9 cosine 9x, that derivative is going to give me back sine of 9x plus 1/2 times, and over here I've got negative cosine of negative x. So the negative cosine is the integral of sine, negative x remains, but we also want to essentially divide by the negative 1 that we have inside there, so that's going to cancel out those negative signs. And this simplifies to negative 1/18 cosine of 9x plus 1/2 cosine of negative x plus c. And if you want, you could use properties of odd and even functions in order to manipulate sine of negative x or cosine of negative x. It's not a necessary step, but if the negative sign bothers you, you could always manipulate it. But this is the final answer that I'm going to leave it with.